going to discuss the properties of determinants, Kramer's rule. So, in this discussion, we will develop some fundamental properties of matrices, and we will use these results to derive a formula for the inverse of an invertible matrix and formulas for the solution of a certain kind of linear system. So let's start our topic with basic properties of determinants. So suppose that um, you have two square matrices. You have a matrix A and matrix B, um, and K is any scalar. So we begin by considering possible relationships between the determinant of A, determinant of B. So if we are going to write that one, that kind of relationship, we could have um, you have the uh, determinant of KA. We could also have the determinant of A plus B. Okay, and of course you have the determinant of AB. Okay, so since a common factor of any row of a matrix can be moved through the determinant sign, and since each of the n rows in k times a has a common factor of k, so it follows that you could have that the determinant of Ka, this one, is equal to the k raised to n times the determinant of A. So for example, if we have this uh, matrix, you have Ka11, Ka21, Ka31, and so on. If we are going to have this one, as we can see, since all of the elements inside the matrix has a factor k, then we could have k cubed. Okay, and then we can have the elements a11, a12, a13, and so on. Unfortunately, no simple relationship exists among the determinant of A, determinant of B, and determinant of A plus B. In particular, we emphasized that a determinant of A plus B will usually not be equal to determinant of A plus determinant of B. Okay, let's have an example. So, suppose you have the matrix A and matrix B. Now, if we are going to have um, AB, not AB, A plus B rather, then our matrix would be you have 4, 3, 3, 8. However, if we are going to get the determinant of A, okay, if we are going to get the determinant of A, this is equal to 1. And the determinant of B is equal to 8. And if we are going to get the determinant of A plus B, this is equal to 23. Therefore, we could say that the determinant of A plus B is not equal to the determinant of A plus the determinant of B. So, in spite of this example, there is a useful relationship concerning sums of determinants that is applicable when the matrices involved are the same except for one row or column. So let's take this one as an example. So calculating the determinants of A and B. Oops. Okay. So if we are going to calculate the determinants of A and B in this case, we can obtain, you have the determinant of A plus the determinant of B is equal to, so you have here A11, A22 minus A12, A21 plus you have um, A11, B22 minus A12, B21, which is equal to A11 times A22 plus B22 minus A12 times A21 plus B21, which is equal to the determinant of, you have uh, A11 and you have A21 plus B21, and here you have A12 and 22 plus B22. Therefore, we could say that the determinant of um, A11, A12, A21, A22 plus the determinant of A11, A12, B21, B22 is equal to the determinant of A11, A21 plus B21, and you have A12, and you have A22 plus B22. Okay. So this is actually a special case, okay, of the general result. Okay. So let's have theorem 2.1.1. So let A, B, and C be n by n matrix that differs only in a single row. Say the rth, and assume that the rth row of C can be obtained by adding the corresponding entries in the rth row of A and B. Then the determinant of C is equal to the determinant of A plus determinant of B. The same result holds for column. Okay, let's take this one as an example. Okay, so here you have the determinant of on the left side is equal to the determinant of the right side. So you have here the sum of the determinants. So I will going to give you this one. Uh, I will leave this one for you to confirm the following equality by evaluating the determinants of the left side and the right side. Okay, so let's have the determinants of a matrix product. So considering the complexity of the formula for determinants and matrix multiplication, it would seem unlikely that a simple relationship should exist between them. Um, this is what makes the simplicity of our next result so surprising. So we will show that if A and B are square matrix of the same size, then the determinant of AB is equal to determinant of A times the determinant of B. Okay, so let's have lemma 2.3.2. If B is a square matrix and the elementary matrix E is an n by n matrix, then the determinant of EB is equal to the determinant of A times the determinant of B. Okay, so if we are going to have this one as a proof, we are going to say that uh, if E results from multiplying the row of identity matrix by K, then by theorem 1.5.1, the E times B results from B by multiplying the corresponding rows by K. So, from the theorem 2.2.3, the first theorem there, we could have that the determinant of EB is equal to K times the determinant of B. But from the theorem 2.2.4, the first theorem stated there, we have that the determinant of E is equal to the K. In other words, if we are going to substitute, then we could have the determinant of EB is equal to the determinant of E times the determinant of B. Okay, so let's have the determinant test for invertibility. So our next theorem provides an important criterion for determining whether a matrix is invertible. It is also um, takes us a step closer in establishing the a formula. So let's start with the theorem 2.3.3. A square matrix A is invertible if and only if the determinant of A is not equal to 0. Okay, so let's have an example. So you have here the determinant uh, test for invertibility. So determine if the A below is invertible. Now, I want you to solve the determinant of A given that the elements of A is 1, 2, 3, 1, 0, 1, and 2, 4, 6. Now, if the determinant of this uh, matrix is 0, then it is not invertible. If the determinant of this matrix is, again, if the determinant of this matrix is 0, then this is not invertible. If the determinant of this matrix is not equal to 0, then it is invertible. Okay, So I want you to verify this example. Theorem 2.3.4. If A and B are square matrix of the same size, then the determinant of A, B is equal to the determinant of A times the determinant of B. So let's have an example. Okay, so considering the matrices, you have A and B. Okay, so in this case, we are going to construct first the AB. So AB, so here, so you have, here you have 2, and then you have 17, then you have uh, 3, and you have 14. Okay. So again, for this example, I am going to leave you the to show the solution, to show the process of how to get the determinant of A, determinant of B, and determinant of AB. So in this case, we could say that the determinant of A is equal to 1. Um, the determinant of B is equal to negative 23, and the determinant of AB is equal to negative 23. Therefore, we could say that the determinant of AB is equal to the determinant of A times the determinant of B. So this guaranteed by the theorem 2.3.4. So the theorem gives a useful relationship between the determinant of invertible matrix and the determinant of its inverse. Okay, so let's have theorem 2.3.5. If A is invertible, then the determinant of its inverse is equal to 1 over determinant of A. Okay, so let's have adjoint of a matrix. Okay, so in a cofactor expansion, we compute the determinant of A by multiplying the entries in the row or column by their cofactors and adding the resulting products. It turns out that if one multiplies the entries in any row by the corresponding cofactors from a different row, the sum of these products is always 0. And that concept is also holds true for columns. So uh, it uh, if we are going to have that one, it follows from theorem 2. 2.3.5 and uh, 2.1.2 that if you can still remember that you have the determinant of uh, a raised to negative 1 is equal to, of course, a over a 1 1, uh, a over a 2 2, and so on to a over a and n. Moreover, by using the adjoint formula, it is possible to show that the a over 1 1 A over 2 2 up to A over A and N are actually the successive diagonal entries of the A raised to negative 1. Okay, or the inverse of the uh, matrix A. Now let's have this example, entries and cofactors from different rows. So let A as a square matrix 3 by 3. Consider the quantity A11 cofactor 31 plus A12 cofactor 32 plus A13 cofactor 33. This is formed by multiplying the entries in the first row by the cofactors of the corresponding entries in the third row and adding the resulting products. We can show that this quantity is equal to 0 by actually having some a trick. Okay, now the trick is we're going to construct a prime. This is a new matrix, okay, replacing the third row of the matrix A with another copy of the first row. So what we have would be something like this. You have A11, A12, A13. You have A21, A22, and A23. Then A11, A12, and A13. Okay. So let our uh, C, you have C prime 3, 1, C prime 3, 2, and C prime 3, 3 be the cofactors of the entries in the third row of the A prime. Since the first two rows of the matrix A and matrix A prime are the same, and since the computations of the cofactor 3, 1, cofactor 3, 2, cofactor 3, 3, uh, cofactor of the prime cofactor 3, 1, prime cofactor 3, 2, and prime cofactor 3, 3 involves only entries from the first two rows of A and A prime. So it follows that you have the what to call this one, uh, cofactor 3, 1 is equal to cofactor of the prime 3, 2, then cofactor not 3, 2, that's 3, 1. Okay, let me correct. And then 3, 2 is equal to cofactor 3, 2, and cofactor 3, 3 equal to prime cofactor 3, 3. Since A prime has two identical rows, it follows that the determinant of A prime is equal to 0. On the other hand, evaluating the determinant of A prime by cofactor expansion along the third row gives us the determinant of A prime is equal to uh, A11 C prime 3, 1 plus A12 C prime 3, 2 plus A13 C prime 3, 3, which is of course, if we are going to substitute the 3 prime, C prime by this, you could have um, A11 C31 plus A12 cofactor 32 plus A13 cofactor 33. Then take note that the determinant of A prime is equal to 0. So in other words, this statement is equal to 0. Okay. So let's have definition. If A is any matrix n by n and the C sub ij is the cofactor of Aij, then the matrix C11, C12 up to C1n and C21, C22 to C2n and up to Cn1, Cn2, and Cnn is called matrix of cofactor from A. The transpose of this matrix is called the adjoint of A and denoted by ADJA. Okay, so that's what we call as the adjoint matrix. Okay, so let's take this one as an example. Determine the adjoint A if the matrix A has that elements. So in this case, okay, again, for this example, I want you to um, verify the numbers by showing the process of getting the uh, uh, necessary information to solve the adjoint of A. So again, taking into the definition that uh, the adjoint of A is the transpose of the matrix of the cofactors. Okay, so I want you to show the process of getting the cofactor 1, 1. Okay, and the cofactor 1, 1 is 12. The cofactor 2, 1 is equal to 4. Cofactor 3, 1 is equal to 1, 2. Cofactor 1, 2 is equal to 6. Cofactor 2, 2 is equal to 2. Cofactor 3, 2 is equal to negative 10. Uh, Cofactor 1, 3 is equal to negative 16. Cofactor 2, 3 is equal to 16. And the cofactor 3, 3 is equal to 16. In other words, matrix of cofactor would be um, you have um, 12, 4, 12, 6 to negative 10, negative 16, 16, and 16. In other words, this is now the adjoint of A. Okay. Not yet. This is, I forgot. Sorry, sorry, sorry. Let me stand corrected. I forgot that to get the adjoint of A, we're going to get the transpose of this matrix. So the adjoint of A is actually you have 12, uh, this is 4, this is 6, This is 2. Uh, this is 12. This is negative 16. This is 16. This is negative 10. And this is 16. And this is now the correct answer, the adjoint of A. Okay, so let's have theorem 2.3.6, inverse of matrix using its adjoint. If A is invertible, then the inverse of A is equal to 1 over the determinant of A times the adjoint of A. Okay, so let's have an example using the adjoint to find the inverse of matrix. Okay, so you have A is equal to 3, 2, negative 1, 1, 6, 3, 2, negative 4, 0. So using the, what they call this one? Using the theorem, so you have that the uh, A, the inverse of A is equal to 1 over the determinant of A times the adjoint of A. Okay, which is, okay, the inverse of A, not the inverse, the determinant of A is, you have, this is equal to 64. So 1 over 64, okay, times the adjoint, okay, of A. So you have cofactor, uh, you have 12, you have here 6, you have negative 16. Again, these are cofactors. So you have uh, uh, 2, 16, 12, negative 10, and 16. Take note, this is the transpose of the cofactor matrix. Okay, and then you have to multiply it. So you have, here you have uh, 12 over 64. Then you have 6 over 64. Then you have negative 16 over 64. Then you have 4 over 64, 2 over 64. Then you have 16 over 64. Then you have 12 over 64, negative 10 over 64, and 16 over 64. And that is now the inverse of A. So let's have Kramer's rule. So in our theorem, in this theorem, um, we the use of formula for the inverse of an invertible matrix to produce the formula which is called Kramer's rule. For the solution of the linear system ax plus b of an equation in n unknowns. In the case where the coefficient matrix is invertible, or equivalently when the determinant of A is not equal to 0. So let's have the theorem 2.3.7, which is the Kramer's rule. So if A is a system of n linear equations in n unknowns such that the determinant of A is not equal to 0, then the system has x sub 1 is equal to the determinant of A sub 1 over determinant of A, x sub 2 is equal to the determinant of A sub 2, over determinant of A up to x sub n is equal to the determinant of A sub n over determinant of A, where A sub j is the matrix obtained by replacing the entries of the jth column of A with the entries of the matrix B is equal to, you have B sub 1, B sub 2 up to B sub n. Okay, so let's have this example using the Kramer's rule to solve the linear system. Okay, so that's the system. So x sub 1 plus 2x sub 3 is equal to 6, negative 3x sub 1 plus 4x sub 2 plus 6x sub 3 equals 30, and negative x sub 1 minus 2x sub 2 plus 3x sub 3 equals 8. Okay, so for the solution using the Kramer's rule, first we could write the um, A is equal to, so you have 1, negative 3, negative 1, 0, 4, negative 2, 2, 6, 3. For A sub 1, we're just going to replace the first column by the by these numbers, the B. So you have 6, 30, 8. Then you have a 0, 4, negative 2, 2, 6, 3. Okay. And for our A sub 2, matrix A sub 2, the second column will be replaced. So you have 1, negative 3, negative 1. You have 6, 30, 8. Then you have 2, 6, 3. And for our A sub 3, the third column. So you have 1, negative 3, negative 1. You have 0, this is 0, 4, negative 2, and then you have 6, 38. Okay, now what we are going to do here is we are now going to use the concept that is being introduced in the previous slide. So in this case, our um, x sub 1 is equal to the determinant of a sub 1 over the determinant of a, which is the determinant of a sub 1 is equal to, you have negative 40, and the determinant of a is equal to 44, which is equal to negative 10 over 11. Same with our x sub 2. So you have the determinant of a sub 2 over the determinant of a, which is equal to determinant of a sub 2. You have 72 over 44, which is equal to 18 over 11. And x sub 3 is equal to the determinant of a3 over the determinant of a, which is equal to, this is 0. So you have determinant of a sub 3 is equal to 152 over 44. 4, which is equal to 38 over 11. Okay, so in other words, our x sub 1 is equal to negative 10 over 11, x sub 2 is equal to 18 over 11, and x sub 3 is equal to 38 over 11. Okay, so I want you to have the step-by-step process of getting the determinant of A, determinant of A sub 1 up to A sub 3. Okay, so let's have equivalence theorem. So you have theorem 2.3.8, the equivalence statement. So in the theorem 1.6.4, we actually listed 5 results that are equivalent to invertibility of matrix A. In those slides, we conclude uh, by merging the theorem 2.3.3 with the list to produce the theorem that relates all the major topics that we have discussed so far. So this would be the equivalent statements. So you have here, if matrix A is an n by n matrix, then the following statements are equivalent. So A is invertible, the AX is equal to 0, has only a trivial solution. The reduced row echelon form of A is the inverse of the inverse, and then A can be expressed as the product of elementary matrices, and you have the AX plus B is consistent for every n by 1 matrix B, and AX equals B has exactly one solution for every n by 1 matrix B. And the last one is the determinant of A is not equal to 0. Okay, so these are the properties of the determinants. So the concept that we have gathered so far in this presentation is, of course, we have a determinant test for invertibility, the matrix of cofactor, the adjoint of matrix, and then we have the Kramer's rule and the equivalent statements about an invertible matrix. So thank you very much.